let's do one more. Okay, limit at infinity of e to the power of this rational function. And limit as t approach, and I don't know, but we can see this one. I can maybe do the shortcut. This is rational function, okay? That's my t. And as x goes to the infinity, we can only look, because it's a ratio of two polynomials, we can look at the degree of the polynomial from the top and the bottom, and it's actually the same, x squared, and x squared is the second degree and second degree. Then we just need a ratio of leading coefficients. 1x squared, negative 1. 1 over negative 1 is negative 1. That means that's the t value. E to the negative 1, or if we wish, 1 over e. That's e actually. Okay, that means that, of course, I didn't really use the limit, but negative 1 is the value of the limit of this function as x goes to infinity. Okay, that means that's how we can compute a little bit more complex limits with the exponential function. And all of them are the exam type and quiz type questions. Okay, actually, let's maybe do this one because it includes trigonometric. That means this will be my last one, and then we can jump to logarithmic. Limit as x goes to pi over 2 from the right hand side, and then we have 3 to the power of tangent of x. That means I do have limit 3 to the power of t. And I don't know how t behaves because t is a limit behavior of tangent of x at pi over 2 from the right hand side. But we know how function tangent behaves. Negative pi over 2, positive pi over 2, and tangent looks like that. And then we have another one. That means we can see from the right hand side, that's the right hand side, function tangent is going down, 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 which means negative infinity. I can use maybe blue color. Okay. And this is negative infinity. And now the final step, exponential function with the base greater than 1 at negative infinity is, it's 0. I can quickly draw it. That's 1, that's 3 to the power of t, and this is my 0. Okay. But that's, we always have to be confident with the trigonometric function, sine, cosine, and tangent. And I think you can find the reference on the reference page in the textbook or the appendix. You can find this information. If you don't remember, but I'm assuming that you do remember. Okay, now the logarithmic function. Logarithmic function is an inverse function to exponential. That means we can see, that's the definition. If we have the exponential expression a to the power of y equals to x, then we can change this to the logarithmic form. Logarithm base a, you can see the same base a of x is y. And again, I can read the other way. How can we understand this? This means that a is taken to the power of y and is giving me x. Okay? A to the power of this number is giving me x. And if we will build a table with the numbers, plot the numbers, the graph of a logarithmic function looks like that. Okay? Of course, you can probably see the line y equals to x because a function and its inverse, if it's plotted in the same Cartesian plane, they always symmetric with respect to this line. Okay? It's like a mirror image. Logarithmic function. Okay, that's logarithmic. I have a slide because I want to talk about the domain. which we can actually see. Okay? Because domain of this function x is that x, you can see what it is. It's kind of like an output, is the range of exponential function, which exponential function had a range positive. We can see the whole function is above the x-axis. The outputs are positive. Now domain is positive for logarithmic. Okay? Domain for the exponential was all of the numbers. Now the range for the logarithmic is all of the numbers. Because if the domain and range like the interchange for function and its inverse. Okay. A little bit of properties of logarithm. When we adding the same base, when we adding two logarithms, we can multiply the inputs. When we subtracting the same base, we have to have the same base, we can divide. Or this property is quite nice and helpful and can simplify lots of calculations. If we have a logarithm, base a, of the quantity x to the power of r, but please note only that input is taken to the power of r, we can put that r, that exponent, in front of the logarithm. And then we can take care possibly of the logarithm. Okay. Cancellation equation means that when I combine, when I make a compound function and its inverse, we always end up with the original input x. That means log base a compound with the inverse function a to the x, it's just x. But we can see, I can put that x, it's easy to prove. And then I end up with log base a of a, which is 1. That's the reason that this is x. This is also easy to prove, but I will just leave it. We can take the log of both sides. Okay, that means that's properties. And now let's look at the natural logarithmic. Since we did have the natural exponential, the same thing will apply for the natural logarithmic. Natural logarithmic function is the function with the base e. You can see this, but I can tell you this is not a proper notation. We will not use like log base e of x. We will actually use a special, a little bit different notation, ln of x. That means when you see ln of x, which means the base is not written, and it's ln, we always have to think that the base is e. We can even see based on the definition. Ln of x is equals to y. This means that e to the power of y, it's giving me x. E to the power of y is giving me x. Ln of e, of course, is 1. Because e to the power of 1, it's giving me back e. Yeah, always is kind of like a circle. And the cancellation equation. Also this, the changing the base of the logarithmic function, we may follow this formula. Okay, and let's maybe try to evaluate this. I wish to have the full classroom of kids and then I will ask the question, but it's okay. Okay, do you think you can help me? What will be the log base 3 of 81? If you know, of course, I think it is 4. I can put that is x, and then the definition is telling me this. 3 to the power of x equals to 81, which means 3 to the power of 4 is 81. Yes, this is, how can I write? Maybe this way. It is 4. Okay, and what about the second one? Log base 25 of 5. I can also put x, 25 to the power of x is 5. That means 25 to the power of what number? It's 5. It's 1/2. Thank you. I can write here 1/2. Because 1/2 is the square root. Square root of 25 is 5. This is 1/2. And what about the last one? I can write this way. You can think about the last one. 10 to the power of x, it's 1/1000. I can write it this way. 1/1000 is 10 to the power of -3. That's when we can see that x must be -3. Because I will cube and I will flip the number and I will get 0.001. Okay, but thank you, Jonathan. It's really, it's really good. I can see that you can calculate quite fast. Good skills. Okay, we'll skip this one. That's me now. A logarithmic function one more time. And the limits. That's me. Let's see this. The same thing. If the base of the logarithmic function is less than 1, of course, not negative numbers. Yes, no negative numbers. Base is always positive. It's the same like for exponential. But we may have a number less than 1 or greater than 1. Less than 1 will result in the shape like this one. Greater than 1 is this one. Okay, it's just the mirror image of the exponential function. And the limits. Now we have to check the end behavior, which means we only can compute a limit at positive infinity and at 0 from the right-hand side. Because domain, it's just positive numbers. That means from 0 to infinity. Behavior at infinity, it's just infinity. We can see function is increasing. And I can tell you, exponential function increases extremely fast. Logarithmic function, which is inverse, is increasing, but really, really slowly. Okay? It is still increasing, still going to the infinity, but extremely slowly. Okay, and the behavior from the 0 from the right-hand side, we can see function is actually going down, negative infinity. And this is opposite. Okay, you can look at this. Now, let's look at few limits. The same like we did for the exponential, now let's do for the logarithmic. How the logarithmic function with the inner value x squared minus 9 behaves at 3 from the right-hand side. Let's do the same thing, limit. Ln, of course, is, that means this is t, ln of t. And t is the quantity x squared minus 9 at 3 from the right-hand side. Actually, I don't have any rational expression, nothing. I can simply substitute 3. 3 squared is 9, 9 minus 9 is 0. Okay, I have no problem. I can use the direct substitution. It's a little bit, actually, can we see, because this is a little bit more, that means it's 0 from the right-hand side, because we do have 3, like 0.1, 3.01. It's a little bit more than 9 when I square. Okay, that means logarithmic function at 0 from the right-hand side. Somebody knows what is the final answer? I can draw the function. That's the logarithmic, always 1. And at 0 from the right-hand side, function is going down. Negative infinity is the final answer. Let's look at this one. Limit as x goes to 5 from the right-hand side, natural log of this quantity. That means this quantity, as always, is t. Limit. Let me use the blue pen. I'm trying to ln of t when t goes and we don't know. T is the behavior of the rational function 1 over quantity x minus 5 as x goes to 5 from the right-hand side. Okay, that's what is this limit? It's 1 over 0. 1 over small is big, but we still have to investigate the sign, positive infinity or negative infinity. Of course, that's not really proper notation, but I always put 0 as a, again, big shortcut for the small number. Okay, because 0 in the denominator doesn't look good. But we know that it's not really 0. This is actually 5.1 minus 5, I will get 0, but I will get positive number. Or I can go even closer. That means it's positive 0, it's positive infinity. And natural logarithmic function at positive infinity, it's also positive infinity. We remember, it's increasing to the infinity really slowly, but it's increasing. Okay, let's maybe do this one, and then we can jump to derivatives. Okay, this is just ln of this quantity. And this quantity, we can see it's similar that I did the shortcut for the exponential. That's rational function 5 plus e x squared over x squared plus 1. That means, again, finding the behavior at infinity, we're looking for the degree of the polynomials, squared, squared, second, second. If it's the same, we're taking a ratio of the leading coefficients. E and 1. Ex squared and 1. E over 1, which of course is E. Okay, that means this is, I can probably write the T notation. I can make a shortcut, but not as fast. And this goes not to the infinity, goes to E. We just figure out at infinity. Okay, that means the final answer is ln of E, and ln of E, it's simply 1. Yeah, it's really nice limit. And please make sure that you know all of the limits that was solved in this session. Yeah? Do not miss any limit. I will skip this. Okay, that means we know how logarithmic and exponential functions behaves. Okay, we know the shape of the graph. We know corresponding limits, of course. That means now let's add a little bit of calculus. That means first of all, logarithmic and exponential functions are nice and smooth curves, continuous, and we don't have any like sharp corners, like sharp edges. That's the reason that we can easily find the derivative. They are differentiable function. That means what I will do, I will start with the general exponential function, a to the x. Okay. That means I will prove like how we actually getting the derivative, where the derivative come from. Okay, that means let's see. I can tell you, you don't really have to repeat, or you don't have to be, you don't have to really know how to prove it. We have to know the final results, which will be the formulas. But let's see, because it's interesting to know where the formulas come from. That means I will start with the definition of the derivative, calculus 1, the h limit. Limit as h goes to 0, f of x plus h minus f of x over h. My function is a to the power of x. F of x plus h will be a to the power of x plus h minus a function a to the x over h. And I will try to simplify, evaluate this limit. Everything that is not h is constant. That means let's try to maybe pull out the constant in front of the limit. Everything what is h, we have to apply the 0, but we can't do at the moment because it's 0 over 0. I can use the property, can you see, a to the power of x plus h, I think a to the power of x plus h, it's simply a multiplication of a to the x, a to the h. Now I have a common factor, a to the h, a to the x, a to the x. I am factoring out. And as I said, this is constant, I can put outside. That means I have this limit. Limit as h goes to 0, a to the h minus 1 over h. Okay, and we have to still evaluate this limit. I don't know if we can easily see, but if x is 0, let's imagine that x is 0 for now. That means if this is 0, this is 0, this is 0. Let's see what's happened. If x is 0, I will have a to the power of h. You see, a to the power of h, a to the power of 1, a to the power of 0, it is 1, and h. That means this box, this limit, it actually end up being a derivative at 0. Okay, we can see how nice it is. It's nice property. Okay, that means it's actually because we can see it's the same thing, but we still have to know what it is. But it's telling me that derivative, I will remove that 0 because I still need x, will be proportional to itself, because this is all, I still didn't compute everything, but this looks like the derivative at 0. That means I have this. Okay, that means this box represents Hamid, you join us, but can you please mute your microphone? Because I see I can hear my voice reflecting. Mute. Okay, now it's good. Okay, that we can see derivative of a to the x is a to the x times value of the derivative at 0. But we still have to, we don't know what is the derivative, okay? That means we still have to like find out what is the value at 0. That means it's definitely proportional to the original function. Okay, let's see. That means what I will do, we will try to investigate this limit, and then we will come back. That's what I have. I took 2 functions, because a is just the general function. I think I took 2 to the x and 3 to the x. And based on these 2 values, just numerical values, I kind of figure out what is this derivative. That means, let's see, 2 to the x and 3 to the x. And I put these values to, that's the ratio from the limit. That's what I'm doing. I'm substituting to this rational expression and this one, the h value. Of course, I can't really put 0. I have to be really close to 0. 0.1, 0.01, 0.001, 0.001, and so on. Okay? And these values, okay, these values are like that. 0.7, 0.69, 0.6, and we can see at some point they are, yes, they are the same. Okay, they will not be greater probably than 0.69. And it's not easy to realize, but I can tell you, these values are natural log of the base, natural log of the other base. Okay, that's what we can see. This is just, if we do, it's just natural log of 2, because 2 was the base. This is natural log of 3. Okay? That means it's based on the numerical. It's not really, we can definitely test this, but it's not really a proper proof. It's just showing you based on the numbers. That means what's happened. It's easy to figure out that this limit, okay, the limit that I'm looking for, is just the natural log of the number that whatever was the base. Now I can, that's the same slide. That means this is simply the value of the derivative at 0 is just ln of the base, ln of a. Okay, that means this is the first formula. Derivative of a to the x is a to the x times ln of a. That means that's the formula that we have to remember, and we have to apply and use it wherever is needed. A to the x, the derivative, we can see we copy the same function, a to the x times ln of a. Okay, now let's look at one more thing. That means we know one formula, right? I can tell you we do have 4 formulas for today, okay? Because we do have exponential function, natural exponential, logarithmic function, natural logarithmic. This is the first one, just the general exponential. Okay, now let's realize something. Again, the same values. If the function is defined as a 2 to the x, we can see this limit is, okay, ln of 2. If the function is defined 3 to the x, this is ln of 3. But looking at the numerical values, ln of 2 is less than 1. ln of 3 is greater than 1. That means mathematicians, they kind of wanted the number to be exactly 1. Exactly 1. That means, what do you think? ln of what number is 1? ln, the natural log of what number is 1? Oh, yes, thank you, Jonathan. It's e. That means that was kind of like also the reason that we do have a number e. That means number e must be between 2 and 3. And in order to have exactly this limit 1, that was the reason that they picked the value 2.7. Of course, we do have different proofs, but that's also one of the things. Yes, they wanted ln of the number to be 1. Can you see my question mark? What number will give me 1? Of course, we know that is e. That means this is the definition. I mean, one of the way to define a number e. Okay? E to the power of h minus 1 over h equals to 1. And soon we will be able to prove this limit, not at the moment. Okay? Because we also have a few things in calculus too that we will still come back. But it's worth to remember, yes, why? Why? Because they wanted this, and this is, of course, derivative at 0 of e to the x. That's derivative at 0, yeah? Another connection. We can see how math is beautiful. It's like lots of connections from the direction that we're not even expecting. Yeah? Always lots of patterns, shapes, connections. Yes, we all connected. Okay, that's me. Now I have just a little bit of summary. We can see the function 2 to the x, 3 to the x, and between actually is e to the x. And the slope, since the slope is the derivative, at 0 is actually 1, exactly 1. But now, what we need a derivative of e to the x. I can follow my general formula. Derivative of exponential function is the same function times ln of the base. But ln of e is 1. That means that's another beautiful property. Derivative of e to the x is just the same function, e to the x. Okay? And I do have another form combining with the chain rule. E to the power of something more, something extra, u function, will be still the same function, e to the u, times du dx. Or if you prefer, eu prime. That's prime. Just different notation. Yes, follow the chain rule. Okay? But this is, that means this is actually, I can write this way, e to the x derivative is e to the x. This is the second formula. Nice and easy. Okay, 2 more. Okay, let's maybe find the derivative, differentiate function e to the power of tangent of x. This means derivative is the same function times derivative of tangent, because that's the inner function. Okay, who can tell me derivative of tangent? Do you remember? Oh, I know that we don't. Oh, we have to remember. Probably when you're watching the session, probably you're answering the question. I know that. Okay, secant square of x. Okay, also calculus 1. Yeah, without this, without algebra skills, without the calculus 1, I don't know if we can go through. Okay. Square root of e to the power of 5x. I don't want to use the square root, I will use the property of the exponents. Okay, that means square root means 1/2. If we have two exponents, we can multiply them together. And now derivative is derivative of e to the power of 5x over 2 is the same function times derivative of the exponent. And this is just 5/2. Okay, so we can see, we can follow the new formula and the chain rule as always. Oh, actually we can do this one because it's not e. 2 to the power of x squared minus 1. Exponential function. Derivative of this function is just the same function times 2 because it's not e. And times 2x, which is derivative of exponent, chain rule. Okay, and ln of 2 is the part of the formula. Okay, that's we okay with this. Now logarithmic. Let's start with the natural logarithmic function because we need two more formulas. Natural logarithmic function and the general. Okay, function is defined ln of x. My job is to find the derivative. And I don't know what is the derivative, but what I can do, I am using my inverse function property or maybe just the definition, whatever way we will define this. Definition of logarithmic. Ln of x equals to y. This means that the base e to the power of y is x. That means I did create an exponential form. And I know what's the derivative of exponential function. That means we're still looking for the derivative of y, dy dx, which is defined like that. But I can use my right-hand side of my screen and applying implicit differentiation, okay, I can possibly get the derivative. That means let's differentiate like it is, left and the right-hand side with respect to x. Derivative of x, of course, is 1. But derivative of e to the power of y will be the same function, e to the power of y times y prime, which is actually dy dx, different notation. Let's solve for dy dx. I will divide by e to the y. The only thing is, I don't know if I like the form of the derivative with respect to y. I have to rewrite this e to the y in terms of x. And can you maybe see on the screen how e to the y is defined? Somewhere. What is e to the y? It's Keith. Thank you. It is x. That means this is the final answer. Oh, okay, I can write this. Derivative of ln of x is simply 1 over x. That's our third formula. Nice and quick, right? Okay. We can nicely see, and thank you for contributing. It's really important, I can tell you. Of course, watching, but attending a live session, it's important. You will see at the end of the semester how you can benefit a lot. Okay, what next? Okay, this is the same thing, but I did add the chain rule. ln of u, the derivative is just 1 over u and times derivative of u, which you can have this notation. 1 over u times u prime. Oh, I mean, that's the same thing. 1 over f times f prime. Okay, that means that's the third formula. And now let's practice a little bit and then the last formula. Okay, ln of sine of x. Derivative of the natural log is just 1 over this quantity times derivative of this quantity. Okay, maybe you can answer this. What's the derivative of sine of x? Yeah. Oh, negative or positive cosine? I think is just positive. Yes, that's mean cosine of x over sine of x. Do you think we can rewrite cosine over sine using different function? I think it's cotangent of x. Really nice derivative. And we can see suddenly from the logarithmic function, we got totally different one, right? No more logarithms. Okay, maybe one more. Ln of the whole quantity, x plus 2 over root x minus 1, x minus 2. X plus 1 over square root of x minus 2. That's what I will do before I will actually rewrite minus. Because when I'm dividing arguments, the numbers, this means that I did have a subtraction of the logarithm. Also, I can rewrite this root as a 1/2. Maybe one more. I can put this 1/2 in front of the logarithm. And as you can see, I did rewrite. Please remember always, especially for the logarithmic and trigonometric also, if the expression looks too complex, try to rewrite, try to simplify before computing a derivative. Okay, and now it's nice and easy. Derivative of ln of x plus 1 is just 1 over x plus 1 times derivative of x plus 1, but it's just 1. Copy constant, derivative of ln of x minus 2, 1 over x minus 2. Done. I can probably combine, maybe common denominator, but that's it. That's the way to, and we can see how nice and quick. Instead of like applying a quotient rule, a chain rule, and that will be too much. Okay. Let's maybe combine 1 over x plus 1, 2 times x minus 2, and then the common denominator, it's x plus 1 times 2, which actually I can put to x minus 2. 2x minus x is x, minus 4 minus 1. Just in case if this will be the final form on the test. Okay. Okay, let's just look at this one because we will need later. Ln of the absolute value of x. This means that we can accept all of the numbers because normally the domain is just positive numbers. I mean, we have to exclude 0. Oh, of course, 0. I was thinking positive and negative numbers. But in order to find, actually I can, okay. In order to do anything with the absolute value, we have to rewrite without the absolute value. This means that we will have ln of x if x is positive, and ln of negative x if x is negative. Because if x is negative, this is still positive value. Okay, and now we can try to differentiate. Derivative of ln of x is just 1 over x. Derivative of ln of negative x is 1 over negative x times negative 1. Because it's inner function. That means 1 over x and actually 1 over x. We can see for x is greater than 0 and less than 0. That means doesn't really matter what is the value, always derivative is 1 over x. And this is the nice proof. Okay. Now let's look at the final formula, general logarithmic function. That means it's not ln anymore, it's just log base a of x. But we remember I showed you the formula that we can actually change the base. I will rewrite the base a like that. ln of x, because I did pick the natural one, and ln of a. We can change, that's the change base. We can put log base b of x log base b of a. That means b could be any number. That's kind of look like 6. Let me put b. Okay? That means we can see I did use, and what I use of course the ln, the base e, okay? Because I know the derivative. That means I did change, I used the changing base formula, I did change the base, and then let's try to take care of this. ln of a is just the constant. That means we don't have to put differentiate constant, put the constant outside, and just differentiate ln of x. And derivative of ln of x, the natural log of x, is just 1 over x. Done. This is our fourth formula. Derivative of the log base a of x, it's still 1 over x. However, we have to multiply by ln of a in the denominator. Okay? And that's the chain rule. 1 over f of x times ln of a times f prime. Follow the chain. Okay. And let's try this one. Log, actually, I didn't type the base. Can you see? And do you possibly know if it's written log, like a log, and base is not written? Do you know what is the base? What's the base supposed to be? It's yes, Jonathan, thank you. It's 10. Actually, I have to be careful because some of the textbooks, they did put 10. Like the old textbooks, they will not put 10. And probably when you look at some engineering, science textbook, you will have something like that. And we have to know that this is 10. Okay? Because I think some countries has the notation log without base written. I think they treat this as a ln, the natural log. That's the reason that we do have confusion. But definitely, if the base is not written, it's 10. Okay? Okay, that means let's differentiate. Log base 10 of 2 plus sine of x. Derivative is just 1 over the quantity, 2 plus sine of x, times ln of 10, because that's base, and still times derivative of the exponent. I can put ln of 10 in front, 2 plus sine of x, derivative of 2 is 0, derivative of sine of x is cosine of x. That we can leave it like that. But you can see I did apply the formula. Do not forget the natural log of the base. Okay, maybe we can do this. 2x times product rule, log of root x. One thing before the derivative, I will try to simplify. And again, log, okay, I think I mean 10. It's x to the power of 1/2. Derivative, 2x, and 1/2 I can put in front. Okay, we know that this could travel in front. And 2.5, of course, is gone. That means I have x log x. That means I did simplify a little bit. And now let's find the derivative. We have to use the product rule. Derivative of x is 1 times log x plus x times derivative of log x. 1 over x and times ln of 10. And I can nicely see x is gone. Log x plus ln, 1 over ln of 10. Okay, that we can see. Always simplify, use the properties, and then apply the formulas. Okay, that means this is the summary of the derivatives. Okay. Natural exponential function, general exponential function, natural exponential function. Natural logarithmic function, general logarithmic function. That means please make sure that's your reference page for this class. Make sure that you know all of the derivatives and you know how to apply them. Okay. Thank you very much for today's session, and you will hear from me next week.